All right. We will get started. Uh, okay. So, yeah. Today we're going to jump into chapter 11. And I know some of you probably just finished up chapter 10 last night. So this might flow quite nicely. It should be fresh in your mind. And that is because, or this will work well because chapter 11 follows right out of chapter 10. And in fact, much of what we're doing is just a slight variation in what we've done in chapter 10. So we're going to continue with the same process. So what we're doing here is following the same 6-step process, following the scientific method. We're being very particular about the ways in which we set up our sampling experiment, and then do that after we've picked our significance and our test statistic and all that. So the same flow remains. The big change in chapter 11 is that the type of question that we are answering, and really with that, so number one, we're opening up new questions that we can tackle, and so we're going to have to make some more decisions along the way. So the big change in chapter 11 as far as kind of the work that's in front of us is, we have some more complicated equations, and we have to make some more decisions to figure out which equation to use. But we don't have to reinvent all of the 6 steps here. Now, yeah. So today I want to outline those decisions, and kind of explain why we use the various equations we do. And then in the kind of the later half of today, I want to just talk more broadly about where this can be applied, and specifically, what type of questions does this open up for us in terms of how we can test different samples. And yeah, so broadly speaking, the big change in chapter 11 is that we're now dealing with 2 samples. We're able to answer questions about whether or not 2 samples, whether the populations they come from are equal or not. And so this is so maybe to kind of foreshadow what we're going to talk about in the second half, this allows us to ask questions about how effective certain treatments can be for a disease. So, so we can run tests and look at a new drug, give that new drug to some people and not to others, and all of a sudden we have 2 groups where we can take a sample from, or those can act as a sample for the broader population, and we can test whether or not one drug is the same as another. And so that has very powerful aspects, or very powerful results. It can be, and so it's used heavily, and now we can talk more broadly about this in a little while, but there's a lot of deviations on this. And so, for instance, the news out this week, I think it was Monday morning, Pfizer released some very promising data about a new vaccine for COVID. And so much of what they're doing is kind of it's another offshoot in step 3 of what we're doing. So the process is very similar. They just have it's a more complex problem that they're answering. So it's not exactly what we're going to learn here, but it's along the same lines. Okay, so much of what we're really into the heart of statistics right now. And so, for instance, in chapter 11, we're learning a new branch of test statistics that answer different questions than we had in chapter 10. And so what I'm trying to explain is that what Pfizer is doing in their vaccine trials is, you can think of it as kind of a different branch off of this step 3. It's one that we're not going to cover in this course, but it's not wildly different than just thinking of it as, okay, we know that there are different questions that we have to answer that lead us to different test results or test statistics. And so we're going to learn some more of those today in this chapter, in chapter 11. Okay. So let's set it up as kind of differentiating it from chapter 10. So first I want to click that button, and let's talk briefly. Again, this is kind of summary. You all just slogged through this, but what were we doing in chapter 10? Well, we were setting up a null and alternative hypothesis, and oftentimes those looked something like this. So we would set up a null as, you know, the mean of the population was equal to some value. Okay, and this was, you know, whether it was a claim or some statement that we made or a guess that we had, and then we were going to test that null, whether or not that was true. So I'm just going to plug in a number. So let's say we were arguing the mean was 15. We then would set up our alternative hypothesis, where the mean was not 15. And I'll try to match the book and use H0 and H1 as best I can, but I'm sure I'll jump back and forth. Okay, so that was really kind of how we set it up. Now, of course, we had variations on that if we wanted to think about a one-sided example, right? It could be something like this, where it's either 15 or greater or less than 15. Yeah, and of course that could be the other way. That could be less than or equal to 15. But largely this is how we set it up. We had a defined value of mu, and what we were going to do is test the sample, or take a sample and test whether or not that sample was far enough away from this fixed point, in this case 15, but whatever we've set that at, determining based on that sample if we thought we had enough evidence that the mean wasn't 15. Now, to do that, we had to make a decision in step 3. Okay, so, well, first of course, we have to set our alpha. Okay, so we had to choose an alpha. But then in step 3, we have to determine which of two routes we're going. Okay, so in chapter 10, there is a question. There's just one question. And this is where it's going to differ in chapter 11. We're going to have 2 questions to deal with. But what it came down to, remember, was, do we know the population standard deviation? And that led us in one of 2 directions. So if we did, of course, hopefully this is familiar by now, if we know that, we're sticking with our familiar z calculation. Right? That's when we know the standard deviation, we can rely upon the z distribution, and that leads us to x bar minus mu sigma over the square root of n. Okay? And we go through the process with that in mind. If we don't, okay, this was the flip side. If we don't, then of course we're left with the t distribution. Okay, still x bar minus mu. And here is where we rely upon s, right? Doing the kind of wavy hand math. We say s is a pretty good estimate for sigma, and so we can plug it in. Okay, and so let's plug it in. Of course, we know that it's not a perfect match, and so here's where the uncertainty comes in. The uncertainty we deal with by using the t distribution, which is generally a fatter distribution than the z distribution. Okay, and that moves around depending on basically our sample size, which is how many degrees of freedom, or roughly, right? So we do that little degrees of freedom is n minus 1, and so we can look up which specific t distribution can we feel comfortable using with a certain size sample. So that was the big decision in chapter 10. Okay, and then depending on which one we did, we just followed the rest of the way. We formulated a decision rule, we take our sample and determine if it's within the rejection region, and so on. Okay, so let's shift over here to chapter 11. Let me get out of the way a little bit, and maybe we'll try to kind of set this up in parallel. So maybe we can see. Now there's going to be a little more to write, so hopefully I can keep this on one one page. So when we set up the null hypothesis now, again, what we're after is we're doing two samples. So we are testing whether or not two underlying populations are the same. So our null hypothesis may look something like, let's assume mu1 is equal to mu2, or can we assume that? Okay, so we'll work with the null hypothesis that these are the same underlying means. So this might be something like, we're not going to say the mean income is 52,000. What we're really saying is that the mean income of these two groups is the same. So maybe we would make a statement like, the mean income of graduates from Hamline Business School is the same as the mean income of people with a Spanish degree or something. Okay, and so what we're setting up is those two means are the same. We haven't said they're both equal to 52,000. We've just said that they are equal to each other. Okay, and we then, of course, the alternative is going to look similar as before, but again, we're comparing these two. Now, the same caveat that we could have a greater than or equal to, right? We could make a statement like Hamline Business School graduates make at least as much on average as Spanish majors do. And then you'd have a greater than or equal to compared to a less than. Okay, but let's stick with just this one example. The two means are equal to each other. Again, we need to set an alpha. Okay, so how much evidence do we need to be able to reject the null? And then here's where it's going to get more complex in our decision making. Okay, so we're going to still make the same. Let me set this up. There's going to be two big questions that we have to answer. The first one is very similar to what we've just done up above. Okay, the first question is, do we know the population standard deviations? So there's two of them here, right? So there's the standard deviation for the first group and the second group. So we have sigma 1 and sigma 2, and what we're asking ourselves is, do we know these? So just like we did it with chapter 10. Again, maybe yes, maybe no. Same kind of caveat. Oftentimes no, but there are cases, right? So these types of methods can also be used in, say, production processes where you might have more of a reason to know the population standard deviation, just like we talked about in chapter 10, right? Maybe the manufacturer or the company that you bought the machinery from tells you the standard deviation is 0.1 centimeters. So or you have enough past evidence to have a good knowledge of it. So there are cases, and when you can know that, so yes, we go right back into our z distribution. Okay, same thing as in chapter 10. We're going to use a z. Okay, now the z is going to look a little different. Number one is that we're going to be talking about two different samples. So we're going to label these x bar 1 and x bar 2. Now, remember, in chapter 10, we're talking about, here's our hypothesized mean of 15, and we have one thing that's moving around. We have the sample mean that's moving around. In chapter 11 here, with the 2 sample, we don't have a set value. We don't have 15. What we have is 2 sample means that are moving around. Okay, but we're interested in the difference between these 2 sample means. Just like in chapter 10, we had mu and the sample mean. We wanted to know the difference. Same thing here, we want to know the difference. So we take the difference of x bar 1 minus x bar 2. That gives us how far apart these two values are. Okay, that's the numerator in the z-score, right? That's always been kind of the point of the numerator of our z-value, is it's some distance, it's some value, and what we're going to do then is put that in terms of how much is stuff moving around. Put it in terms of a standard deviation. Okay, and that's what we've done in chapter 10. over here we did sigma divided by square root of n, giving a feel as to how much that x bar typically moves around, right? We're randomly sampling, so we know it's not always in the same spot. It jumps around. So the denominator is always telling us, okay, give me a sense as to how much it moves around. That will help me interpret how big this distance is. Same thing in chapter 11. Two things moving around, so that how do we measure how much they move around? That gets a little more complicated. But the point is the same. The denominator is going to tell us how much does this distance between these two samples typically move around. So the equation becomes sigma 1 squared divided by n1 plus sigma 2 squared divided by n2. Okay, and there we have, this is the full z score for this scenario. Okay, so a little more cumbersome, a few more numbers to plug in. But you can think of it actually, so this might help it sink in for a few people. Notice down here, I don't have, in the new version, I have sigma 1 squared and sigma 2 squared. But notice they're within the square root. So actually, if we go back down to chapter 10, notice that this bottom part, I could rewrite that as the square root of sigma squared over n, right? And I could factor that out. So just as kind of a way to highlight that these really are, how do I point at them both? These are really very similar in theory here. Right, so it's just we can't do that same pulling the squared versions out because of this addition sign up here. Okay, so mathematically visually they look a little bit different, but mathematically they're very closely related. I'm going to get rid of that just because we don't write it in that form and we don't need more equations on the screen. Okay, so the other thing to note, we have N1 and N2, right? So we have two sample sizes. We're taking two samples, so we have an N1 and N2. They could be the same, but they don't have to be. Okay, so that's the Z. That's if we've chosen or decided that we do know those underlying standard deviations. What if we don't? Well, as you probably can guess, we're headed to the T distribution. I'm going to kind of zip this over here because we are in the T, but we have to make another choice. So here's where kind of some more complexity comes into chapter 11. So what are we deciding now? So we have two underlying populations. We have mu1 and mu2. We've already said we have sigma 1 and sigma 2, right? We have how much do these populations move around. We've said we don't know what they are, but what we haven't said yet is whether or not we think they're the same. So if we think that sigma 1 is equal to sigma 2, we're going to go with a different equation. So this second question is sigma 1 equal to sigma 2? And if it is, we're going to plug in one value for that. Okay, you can think of, so this is yes. We're gonna use them both to plug in a single value. We're gonna use what am I saying? Plugging in both. We're going to use S's, right? So what happens in chapter 10 when we don't know sigma? We use S to estimate it. That's why we're building the T distribution. Similarly, here in chapter 11, we don't know sigma 1 and sigma 2, but what do we know? We know S1 and S2. We have two samples. We take the first sample, we get an X bar 1. We also can get an S1. That's our estimate for sigma 1. Same thing for the second sample. So what this question says is, do we think sigma 1 and sigma 2 are the same? If they are, we'll do a certain calculation to use that information. That's kind of extra information there. Okay, so let's start with the case where we don't think they're the same. We can't justify that assumption. So this is going to be a cleaner version of the T statistic. Now, it comes with a caveat that it's going to force us to make a pretty gross calculation for degrees of freedom. But the T distribution simply, just like we did in chapter 10, we're going to plug in s's. So this becomes x bar 1 minus x bar 2, right? Same, talking about the distance between those two. And just like we did in chapter 10, we're going to plug in s's. So we're going to say s1 squared over n1 plus s2 squared over n2. Yeah. So very straightforward. We're doing the exact same thing as we did in chapter 10. Now in chapter 10, get out of the way here, we did a degrees of freedom of n minus 1. Pretty simple. Less simple here in chapter, just get rid of that. Less simple here in chapter, where are we in? 11. So the degrees of freedom, I'm just going to kind of scribble it down here. It's gross. It's in your book. It's not difficult in the sense that all it is 4 different numbers that we need to plug in there. It's just there's a lot of places to mess up the calculation. We'll say that. Okay, so the degrees of freedom is s1 squared over n1 plus s2 squared over n2. That's all squared. And then that is divided by s1 squared over n1 over n1 minus 1. Again, you obviously never need to memorize this. Over n2 squared, and this might not even be legible. There's so much going on. But it's behind a screen. So it looks something like this. Okay, so it's very gross. It's the gross degrees of freedom calculation. So that's kind of the downside. So as far as your process for working on homework and whatnot, if you get the easy t distribution, if you're over here with the easy, nice, clean t distribution, that means you got to do a difficult degrees of freedom. The flip side is the degrees of freedom. Let me just shortcut the degrees of freedom. If we jump back up here and say, yeah, we think they're from the same underlying population standard deviation, you get a really nice, clean degrees of freedom. Its degrees of freedom is n1 plus n2 minus 2. So that's great. But we get a gross t calculation. Okay, so you don't get to win either way, sadly. So let's go back up and just finish out this tree. So we have one other decision here, or the other side of this decision. Let's say we think they are. So what we're going to refer to that as pooled. So we're going to calculate the pooled standard deviation. Or really, we're going to calculate the pooled variance. Okay, so the squared. So we're going to calculate, I'm going to come down here and do that first. So SP squared. We're going to calculate this version of a variance. Now, the theory here is that we're saying these come from the same underlying sigma. Okay, and what was our goal here all the way back to chapter 10? S is a good guess for sigma. So if both of these are the same sigma, that means really we have 2 guesses at what sigma is, right? And that should be a better guess than one of them by themselves. Okay, so again, S is not sigma exactly. It's in the ballpark, or that's kind of what we're assuming, right? It's a good guess. It's unbiased guess for what sigma is. So let's use both guesses. We have an S1 and we have an S2. We don't know what sigma is, but now we have 2 guesses. So let's use all of that information and kind of smush them together. And we're going to rely upon a weighted average. Okay, so rewinding all the way back to chapter 3 or 4, whenever we first came across weighted averages, here it is again. We're putting these together, our 2 guesses, and we're weighting them based on basically how big of a sample did we take from each. So if we took, 100, if our sample size if N1 was 100 and N2 was 20, we think that the N1 was a better guess, or sorry, the S1 was a better guess. So we're going to weight that more. Okay, so we're going to lean more on the S with a higher sample size. So that's why we're going through this kind of process. We're not just taking like the midpoint, right? If the sample sizes were equal, we basically take the midpoint. S1's over here, S2's here, and we say, yeah, sigma's probably right in between. Because we don't always have equal sample sizes, we'll weight them. Okay, so that equation looks like this. Again, it's obviously in your book. So you don't necessarily have to memorize this, but it's, once you kind of understand that we're taking a weighted average, it starts to make some sense. So we're taking a weighted average of the variances, actually, right? So you can see that S1 squared is plugged in here. And then again, on the bottom is that we're dividing by the kind of that degrees of freedom. So really we're taking a weighted average in terms of degrees of freedom. Just note that it's N1 minus 1 and not just N1. But the concept there is a weighted average based on the sample size. So that's our SP. So we think that that's a better guess for what sigma is. And so we're going to use that. And so jumping back up here, I might just change the color here a little bit so that kind of tucked away in the middle. So T then is, again, the top is going to be the same, x bar 1 minus x bar 2. And the bottom, again, how much did this stuff move around? We're able to change this a little bit, and really what we're doing, let me just say it's SP squared over N1 plus SP squared over N2. Okay, so we're really plugging in that SP, that pooled variance, in place of each sigma. Now the book has it written as follows, which is fine. I just think it's a little clearer to understand when we put it in terms of this, that we're really plugging in that pooled version. Now, when you work with it, it's fine to have it this way. So SP squared, we're just factoring out that SP. Okay, so this is the version that is written in the book, and it is correct. I just wanted to write it in this case because it matches more closely what we've done in these other cases. So even the Z, or over here with the other T. Okay, so really the big change here, this decision is is sigma 1 equal to sigma 2. If it is, let's then take a guess with SP and plug that in for both. Okay, so this is the framework for chapter 11. I know there's a lot going on, but really it comes down to two questions. And again, much of what we're doing in statistics is figuring out which equation to plug in. And that's what you had to do in chapter 10. It's what we have to do in chapter 11. It's what we have to do kind of all the time. Yeah, and as I mentioned, again, this is all kind of one. If you think of a larger tree, this is one big branch, and we're into 2 sample testing, and we have to decide which out of there we're going to pull from. And there's a whole broader context of different test statistics that you can get to, and you end up in places where you can do vaccine testing. So towards the end here, we'll just kind of plug in some values for kind of do an example. But first, I want to talk more broadly about what we're doing here in general in terms of 2 sample tests. And to do that, let's just talk about first. We're going to start with kind of what is ideally what we would have. I'm going to switch to a new. Let's just blow that back up a little bit. Okay, so we want to be able to test precisely some interesting questions, and if we can, let's walk through kind of an example or a broad context. So there's a method called what's called randomized controlled trials. Okay, you'll hear these called RCTs. Okay, you may have heard these pop up, over the last number of months as new drugs or new treatments for COVID were being discussed. There's a lot of clamor that we need RCTs and we can't rely upon anecdotal evidence. And really, so what we're going to talk about is what are those RCTs, okay? And just to preface, if you're in the kind of a techie world, so the degrees of freedom for no sigma, I'm just getting a question from Andrew. For no sigma, are you thinking for the Z score? So just to clarify, maybe this is what we're after. We don't need, for the Z, we don't need a degrees of freedom. So there's no degrees of freedom necessary here because we're just with for the T. So for the T, it's this if we don't know the sigmas, or if we don't think they're the same, it ends up, this is our degrees of freedom calculation. Okay, so it's one of these two. So if you think that they're the same, if we're in yes, then we do this. This is kind of, I realize the confusion might be that, so we kind of have a dividing line here. Okay, so if we're in the yes, then we do this form of the T, which requires us to calculate the pooled variance. Okay, and the degrees of freedom is simple. Okay, so that's the nice part. If you're going through this gross pooled variance, you get the nice clean degrees of freedom. If we're over here in the no, the T value is easy to calculate, but the degrees of freedom is really gross. Okay, so you get one easy and one hard. Okay. So if you're in the tech world, or if you read tech blogs, or if you're into that world, or digital stuff, you'll hear it, or even in business sometimes you'll hear it referred to as A/B testing. Okay, but it's basically the same concept, putting things into either A or B, testing whether or not they're the same or they result in the same outcomes. So just another kind of term for basically the same thing. Now, so what is an RCT, and why is it the gold standard for many methods that we'd like to do, or many experiments that we'd like to do? Well, at the heart of it is this randomization. Okay, so just like as we've been talking all along, this concept of randomizing us, being able to say that yes, our sample provides a good unbiased estimate for the population is really what we're after, right? And so this randomization allows for that. So think about back to trying to take a sample height on campus. We had those issues if we were to take that sample outside of the divers, right? The divers are coming out from class or from practice, and we get too many divers into our sample. I double checked, divers are shorter on average, or at least Olympic divers are. So I wasn't wildly off base. So if we do that, we have a problem because our sample doesn't give a good representation of the population. Same thing is true here with two samples and basically all across statistics. If we have issues in our sampling, we can't rely upon the results. So this randomization, this RCTs, does a very clean randomization for us. And so this is why we generally kind of default and say, can we do something like an RCT? If we can't, how do we deal with the problems that are posed by not being able to do this? Now, on the plus side, these are fairly easy to set up for things like medical testing. Okay. So let's talk about kind of an example. I think that'll help set up what are these RCTs. So let's say we have a new drug and we think this might help patients, maybe hospitalized patients with COVID. We have somebody's developed this drug, or we're using an old drug, but we have kind of a rationale as to why it might work. So we're going to set up an RCT, and what that's going to do is split people into one of two groups. We're going to randomly put people into one of two groups. Now, we're going to still go through the same process. We're going to say, I think, our null hypothesis is that the mean outcome for those in the treatment group is equal to those in the control group. Okay, so I'm already kind of jumping ahead and using the language of treatment and control. This falls out of the medical literature. And so we'll set up our hypothesis much the same as we've been working on. Of course, our null hypothesis being that they're not equal. Of course, we can set it up one-sided as well. But how are we going to test this? What we're going to do is we're going to take our group of people. So let's say we have a bunch of people that are sick. Okay, they all need to be hospitalized, so they're laying on their backs. Okay, so we have a bunch of people, and what are we going to do? They've all been hospitalized, and they're ready for treatment. So typically what happens is that, especially with medical scenarios, is that we're going to give the test, or that we're going to give the treatment to some of the patients. And for the other patients, we're going to do the typical treatment. Okay, so it's not that we don't give them anything. We don't say, okay, good luck. We give them what's typically done, the standard course of practice. And what's important is that we're going to randomize who gets what. So some of the people are going to be plopped into, again, to use the terminology from medicine, they're going to be in the treatment group. And some of the people are going to go in the control. Okay, this is the randomized controlled. Okay, so some of the people, we might split it in half. Sometimes we don't. Sometimes there's some reasons to have a few more people in one group or the other. But basically we can think of it as randomly separating them, and maybe we put 140 in the treatment and 120 in the control. And so now we have a sample. So if we think about the population of all people that would be hospitalized with COVID, we now have a sample of 140 people getting this new treatment, and we have a sample of 120 people getting the typical treatment. Okay, and obviously with COVID, there's a lot of typical treatments, so we need to clarify exactly what that is. And to be more clear, we can oftentimes make multiple controls and all that. But on the base level, this is what we're doing. We're saying, here's a new treatment, here's a control. Now, a few other things to talk about here. So when we do it, we want to be very careful that we're not accidentally biasing our results. So a couple things we do typically. You might have heard the term placebo. So a placebo, or the placebo effect, maybe you've heard. So a placebo is, we want to make sure that the people getting the control don't know that they're getting the control, and the treatment don't necessarily know that they're getting the treatment. So typically, if you were to be here in this, if you were one of these people, they would say, you're entering into a new study. We're going to, they'd be clear that there's a chance that you get the treatment, a chance you don't get the control, or that you don't get the treatment, but you are not going to know, right? Because what we want to do is avoid something called the placebo, where simply the act of getting the new treatment, maybe psychologically it helps you. You get, there's a lot of theories as to why the placebo effect holds true, but you might just be excited that you're getting the new treatment, and it revs up your kind of your hope comes back, and that can be helpful in and of itself. Positive thinking and hopefulness can help you fight off maybe the infection or something like that. Okay, so to counteract that, we give both groups a pill. So the placebo typically, or a lot of times, if you're getting a pill for the treatment, you'll get basically a sugar pill in the control. That way the patient doesn't know what they've gotten. So that helps it be a blind, what's called a blind study. So the patient is blind to whether or not they got the treatment in the control. To push this one step further, what we typically do is what's called a double blind. And so both the patient and the administrator of the treatment don't know. So the nurse or the PA, the NP, or somebody administering the care, the MD, also doesn't know which treatment or control the individual patients are getting. Okay, again, that's to make sure that we're not giving different treatment or different care. We're giving a treatment or a control, but we also are caring for these individuals. So we want to make sure that, you know, the doctors aren't more excited to treat. I don't know if excited is the right term, but more willing to do other courses of action if they knew that they were getting the control, for instance. So all of that is stuff that we do need to bear in mind when we're designing these. So once we've done this, though, again, we now have 2 samples, and we can measure the outcomes. So far, I've just said the mu t is equal to mu c. So what is mu? Well, before we, again, administer all this, we're going to outline what are the outcomes that we're interested in. So a lot of times this is something like, or in our case, maybe we are interested in, these are hospitalized patients. So how long until they are, released from the hospital? So we might measure something like the length of stay in the hospital. We could have a mean length of stay, and we could measure whether or not patients that got the treatment stay the same length as patients that got the control. You could do length of illness, you know, until symptoms are gone. You can do things like death rate, right? So that we would switch the mechanism a little bit, right? Because that's going to be a proportion. So we can do proportions in this just like we could in previous, right? So, but it won't be a mu here. We'd be measuring, a pi. We can adjust this in other directions, right? So actually, a lot of time, or most recently with these types of drug trials. So for instance, remdesivir. I didn't say that right. That was shown to have some effect in getting patients out of the hospital sooner, but they used the median. Okay, and so we've talked about this for a couple chapters, that we're relying upon the mean, and we're kind of working through the understanding of measuring the differences in means. We can do this a whole process with medians. It's just the math is a little different. Okay, so nothing grand changes. It's just slightly different equations. And so, we could do something like that with length of stay as well. So all that is to say, we would set up beforehand that we're interested in whether or not this new treatment gets people out of the hospital earlier, right? And so we set it up as though it doesn't. The mean hospital stay is the same, and then we can test that. Okay, so we have a sample, and we get X bar 1, X bar 2, S1, S2. I'm trying to think if there's... so let's zoom out from just this kind of health medical field testing. This has applications all across the board. So there's, for instance, there's a branch of economics related to development economics, where we study how best to assist or where best to spend aid money, for instance, in the developing world. So you might be worried about education. How do we help students become educated? Do they need things like textbooks? Are class sizes important? Teacher attendance important? Deworming. Sometimes a simple act of giving deworming pills can be effective. So these are methods that we can set up randomized control trials. There is there's a interesting paper. Actually, you can listened to it on Freakonomics a number of years ago. Professor Glevy out of the U of M, just down the road, does a study with some co-authors on the effect of glasses. How much do glasses impact educational attainment for students? They did the study in rural China and basically randomized who got glasses and who didn't. Now, again, there's some variation here in that they randomized which schools they were going to give glasses. So some schools, all the students that needed glasses were made available to them, and some schools they weren't, to avoid kind of issues about kind of how we socially learn from one another. But the main concept there is a randomization of who gets the treatment and who doesn't. And in that case, you might think of, mu is not length of hospital stay, but maybe it's test scores or graduation rates or things like that. Now, what I want to talk about briefly then is this obviously brings up concerns about ethics, the ethics of these types of RCTs or this type of testing. And specifically, we're playing around with what people are given, and whether it's medical treatments or access to textbooks or something like that. And so the way it's typically done nowadays is that, if you're doing one of these types of tests, is that you have to pass what's called IRB approval from the university. And this is an independent board that verifies that there's no ethical concerns behind them. So that's kind of the process we go to double check. But what types of things do we need? So for instance, in the glasses scenario, we might be concerned that we're kind of we're playing God in terms of what students get these things that they need and what students didn't. And the way we typically overcome that is, the students that didn't get them, they later did get them. So typically, I think in that study, they measured the outcomes after a year, and then they went into the schools that didn't randomly get the glasses, and they made them available as well. And so in some sense, you can think about none of the students were going to get the glasses. And so all we've done is we've given glasses to them, but a year apart, so that we can measure the effect. And so typically, we've done much better at dealing with those ethical concerns. Obviously, there are a lot of scenarios, even just 30, 40, 50 years ago, where there's some pretty shady stuff happening in terms of these types of testing, especially with medical drugs and stuff like that, going into impoverished communities and administering, drugs that potentially have harmful side effects, right? So in the glasses, there's probably not a big side effect of wearing glasses, but for drugs there can be. Okay, and so that's why you'll see, they're volunteer. Even for the vaccine trials, it's volunteer, which is somewhat helpful. Although you still want to make sure that people are aware of the risks that they're taking on. I mentioned A/B testing, so I just want to talk a little bit more about that. So this is that tech world, kind of whatever the broader term for that now is, but if we think about these RCTs in general, and this is a very clean way to get to samples. The difficult part in, say, you're going to rural China and developing all this is to adequately randomize this. Now, where is it really easy to randomize across large sample sizes and really quickly? Excuse me, and keep track of who got what treatment and control? Well, take out your smartphone and open up Facebook or whatever app you use now that, I don't know, you're too young for Facebook. But when you open up Facebook, assuming you have an account, just to check on what your grandparents are doing, when you open that up, there is a specific color of blue that you're met with. Okay, and that blue is not by accident. Okay, and this is a silly example, but let's think about how we would design a RCT. We have millions of users opening up Facebook every day. Let's just grab 200,000 of them and tweak that color a little bit. What happens to their mean time spent on the app? How many ads do they click on? and so on, right? And so we could measure all of that very quickly, a couple lines of code. And so this type of rapidly doing this A/B testing, or basically an RCT, is quite easy in the tech world, across all kinds of apps or computer programs and whatnot. I never finished, but Netflix had that, what is it called? Social Dilemma or something. And I think they briefly start to touch on this kind of concept, or they get into it. I don't know if they specifically talk about, A/B testing, but the ethical concerns are probably there too, right? So what are these companies, how are they manipulating our, desires and ad choices and all that type of stuff? Doesn't really have IRB, the same way that a university would kind of oversee, somebody trying to do a test. It's not really probably the same level of oversight. So those ethical concerns are still there as far as the manipulation through this type of treatment and control. So yeah. What did I fail to talk about? So just yeah, so now that we've kind of talked about these RCTs and really what we're doing in chapter 11, what we've seen in the vaccine trial is not quite what we're doing here. It is an RCT in terms of there's a treatment and control. It's just that the outcome that they're measuring is not a mean, okay? And really, it's kind of a, and yeah, it's a more complicated scenario, but really it's a variation in step 3. Okay, what type of statistic? How do we set this up? There's still a null hypothesis. There's a level of significance. It's more about the test statistic and really somewhat more about kind of how do we determine what the outcomes that we're interested in are. Yeah, so real briefly, I'm just going to finish up by walking through, an example here, and I might be able to fit it on the same screen. So let's say we did this type of a test, and we said, so what are we going to get? We're going to get an x1, x bar 1, right? And I'm going to actually use the notation xt and xc. Now, some people will leave it in x1 and x2. I find it more convenient or more clear to keep it in treatment and control, or somehow label, in that sense, because I can't register 1 and 2s. So we'll get an x bar 1 and an x bar 2, or an xt and an xc. And so maybe we find 10.4 and 11.6. Okay, let's say that's the mean length of hospital stay. We would also, again, get an S1. So let's say that's 3. And here I am jumping back and forth. So the S for the treatment is 3, and the S for the control is 4. Okay? And we probably don't know, so we have to decide. Do we know the underlying population standard deviation? Probably not. So let's go with a T. So we've already branched and we're saying T distribution. And now we have to decide if we think they come from the same underlying standard deviation. Again, let's assume they don't. So mu1 is not equal to, not mu1, sigma 1 is not equal to sigma 2, or at least we can't make that assumption. So that leads us to the following T. Right, and that, just to clarify, we've basically gone down to here. Okay, and so T is then x bar 1 minus x bar 2. Now, just for sake of time, I'm going a little bit out of order, right? I'm not formulating the decision rule. We could do that, but I just want to have you see the T in action. So S1 squared over N1 plus S2 squared over N2. And that is going to be 10.4 minus, what did I call it? 10.4 minus 11.6. And that's all over this little grosser. So 3 squared over 140 plus 4 squared over 120. Okay, and that becomes what, negative 1.2, and I think the bottom, you can double check my math, but that's 0.445, which leads us to a t value of negative 2.699, or basically negative 2.7. Okay, so we have a t value, and again, now we can look up whether or not that's significantly different. Of course, if we had already done step 4, we would know, but we're in a t world, right? So we've found a t distribution, but we need degrees of freedom. Okay, so we don't know what that is. It's not as simple. In this case, we have to plug in the gross, the gross values. Okay, and again, it's mostly plug and play. I'll write it out here, or at least the beginning of it. So it's all of that top stuff squared. And then I'm going to run out of space here, but 139. Anyway, you plug all that in, you can verify it comes out to about 229. It might be 228, something we round or we round down. So it might be a little over 229. And that's our degrees of freedom. Okay, so it's not often wildly different than n1 plus n2 to minus 2, right? In that case, this would be 258. This is a little lower in degrees of freedom. Why is that? Well, we need a little more. We have a little more uncertainty, right? In this case, we're saying we don't know what mu. Keep jumping to mu. We don't know what sigma 1 and sigma 2 are. We're taking an estimate for both. So we got more moving parts. So we're going to keep the degrees of freedom a little lower than if we thought that they were the same and we're taking a good guess at it. We're using S1 and S2 to guess what the single sigma is. We can be a little more sure. So we use a degrees of freedom of N1 plus S2, N1 plus N2 minus 2. Okay, so that's why we go through this growth calculation for degrees of freedom. We need to maintain a little more uncertainty. In this case, it doesn't really matter because we have such a high degrees of freedom that it's not going to wildly alter. We would go to the t value and say, you know, the t for a two-sided 5%. Let's say we're using 5% significance is 1.972. And so, in any case, we have found enough evidence to reject this null. Okay, and so this is, we would then say, we have reason to believe that the two mu's are not equal. We think that this treatment may be effective in lowering the time spent in the hospital. Okay, and so we might advocate for probably, you know, this might not be the final step. So maybe this leads us to the next trial. Now, this is not the only outcome we would want to measure, and oftentimes we're also measuring negative side effects, right? So we would want to be measuring, okay, what proportion of people in the treatment and control have some form of a negative impact from this. So we're kind of juggling a few different tests at once. Yeah, and now the last little thing I want to mention is that we found here, because I made up the numbers, but we found a little over a day difference in hospital stay. That has practical significance, right? That could be quite helpful. We could have found a statistically significant difference. So let's say probably with a little larger sample. Maybe we had 1,000 people in each the treatment and control. It's possible we would find enough evidence to reject the null in a scenario where the difference between the two X bars was like 0.2 days. We would then need to contend with, does this matter? Does this difference matter? Does it practically matter? And that's a separate question in terms of, it's not just can we reject the null, but we would want to know, is this worth, administering, given that it's only changing, checkout times by 2 hours. And so that's a different question, and it involves weighing the the positives here 2 hours earlier versus the possible negative side effects. So that's something that we'll need to contend with in the future as well. So that is a lot of information for you to take in today. We'll be back on Friday. We'll look at some examples, and we'll also we'll look at some examples probably both on the chalkboard and maybe even in Excel. So we'll talk to you then. I'll stick on for a few minutes, and then also remember I have office hours later today. So if you want to jump on at between 1:30 and 2:30, feel free.